Hello, everyone. I'm Hongji a PhD student working with Professor Zhou from the Department of AMS and IACS. This is a cooperation project with Professor Levine from the Department of Chemistry and IACS. The theme is the A-square ERI matrices in NP2 theory. The hierarchical matrices and A-square matrices are designed to store safe storage for large diagonal dominant matrices with some low-rank properties. We can see from this picture. And the diagonal part is important, so we store them as full matrices. And for the far places, we cut them into large blocks and do the low-rank approximation to these things, such as this green block. ERI tensor is such a tensor with these properties, so we plan to apply the hierarchical matrices to it. NP2 theory is a widely used chemistry theory involving the calculation of ERI tensor. So by testing the results of NP2 theory, we can see the performance of our A-square approximation of the ERI tensor. And this algorithm is the process of our project. Firstly, given an ERI tensor, we do the A-square form calculation. We transform the tensor into this form, and then we do index transformation. This process is the most important part in NP2 theory, where the basis functions of different atoms can be mixed together. And then after the index transformation, we get a new A-square matrices, and we do Frobenius inner product between the old and the new matrices, and we can calculate the NP2 energy. I wrote a toy model code in MATLAB to test the complexity, and normally the NP2 theory requires the complexity of O(n) to the 4th. But with the A-square form, it can be reduced to O(n) to the cube. And then our test result is that it's really approximately O(n) cube. So this is a promising result. There are also other approximating methods such as DF or THD. The difference is that in their method, the ERI tensor is approximated as a whole, while in our method, we just cut them into smaller matrices and do low-rank transformation to these smaller blocks. We have already analyzed the computational complexity for the mathematical model, and now we plan to further test the complexity to the real ERI tensors and see the results. If the stability and accuracy are promising, we will further explore the further compression of the tensor into such as 4-dimensional or other compression method. That's all.
Do you see a path to getting down to close to linear scaling for really big systems?
In principle, the A-square matrix is scaling linearly with this side. This size is n squared, and the storage is linear, but the time complexity will be O(n) cube or this to the power of 3 over 2. Okay. I'm sorry, can you speak louder?
Yeah, is this structure also useful to make matrices?
Yeah, this is a mathematical tool, and we just find that it might be useful to ERI tensor, but it is developed in linear algebra